Okay, so 3 sections today. First one is conditional proof. What exactly is a conditional proof? Method for deriving a conditional statement, either the conclusion or some intermediate line, that offers the usual advantage of being both shorter and simpler than the direct method. It's kind of a shortcut, nice shortcut, and it completes the rules of inference because it helps you with the proofs, helps you to achieve the goal, to prove your argument. So the method consists of assuming the antecedent of the required conditional statement on one line and then deriving the consequent on the subsequent line. Right? So this is a good example which we will start with. Let's say this is what you have. Anyway, so in this case, when you look at the conclusion is a conditional statement. And conditional proof, of course, works for conditional statement. It doesn't actually have to be the conclusion, but it starts with the conclusion. So using the direct method to derive the conclusion of this argument would require a proof having at least 12 lines, which is very long and complicated. But if we do the shortcut, we can achieve it much faster than that. So looking at the conclusion in this case, let us suppose that A. Let us just assume A. So the way it works is you have to draw additional line here, and your 3 would not be lining up on this side because it's conditional, right? And then you just assume in A. That's how it starts. So let's just look at the proof. Yeah. ACP means assume conditional proof. So that's the beginning of your sequence. You assume in conditional proof. Then once you assume that, you are looking here and using whatever you have on the right side in the same way as we did before. So for example, between line and 3, you do have the modus ponens. Right? So that would immediately give you B and C. Then you can simplify it, just B drop in C. Then you can add, remember that's another valid way to do it, B or D. You're adding D here, so that's addition. We started it higher up. But anyway, and you see, once you have B and D here, that gives you E. That's just modus ponens. 2 and 6 modus ponens. Now that showed you that based on your 2 premises, assuming A does actually lead you to E. And since A does lead you to E, which means that this is true, you can now conclude that that is indeed the true conclusion, or the valid conclusion. It's not, we don't know if it's true, but assuming it is true, that would lead to a valid conclusion. And on this line, you're writing that from 3 to 7, you did conditional proof. See, that's just to let you know, like this is how you derive line 8. Line 8 goes back here, so this is discharging the conditional proof. Discharging means that you are no longer working within this assumption. Now you can go back to the actual argument, and your conclusion is not just assumed, it actually follows from these 2 premises. Okay, so that's basically the idea for conditional proof. So just step by step, first step in constructing conditional proof to decide what should be assumed on the first line of the conditional sequence. The clue is always provided by the conditional statement to be obtained in the end. the antecedent of this statement is what is to be assumed. So in this case, this, right? This is why we started with A. For example, if the statement was K and L, therefore M, K and L would be instead of A in this case. And you're writing your ACP, assume condition. Second step is once the initial assumption has been made, the second step is to derive the consequent of the desired conditional statement at the end of the sequence. So in this case, you are heading towards T, right? And you're working with your premises here. That's what you are using to get there. So you're trying to figure out what's the best way. In this case, the best way was to do first mode exponents, then simplify, then add, and then you get another antecedent here, which leads you. So again, you can think about it kind of backwards. I need to get E in the end. To get E in the end, I do need this. How can I get this from A and this? Well, I will obviously do the first step. That would always be the first step because there's really no A here, so there's nothing else you can do, right? But since you're working towards this, then the other two steps become evident that you should simplify, remove your C, and add your D, so that it would give you this antecedent. But obviously, in each case, the sequence would be a little different because you have to look at what you have and what are you trying to achieve. We are still using all the same rules, but now we are kind of using them in a slightly different way. And the third and final step is to discharge the conditional sequence. So this is here, right? This is where you discharge it. Because you cannot finish with the conditional. The antecedent of this conditional statement is whatever appears on the first line of the conditional sequence, and the consequent is whatever appears on the last line. So antecedent and consequent in this case would be A and E. And we basically in this case we have just proven that our conditional does indeed follow from these two premises. That's what we did. But for example, if A or B is on the first line and C and D is on the last, then the sequence to discharge would be going from A or B to C and D. Discharging line is always written adjacent to the original margin and is tagged with abbreviation CP. And you are writing which lines you are using here from 3 to 7. You can also use it within an argument for other lines. It doesn't have to be a conclusion. So this is an example how you can work with other conditionals. Here you don't have the conditional in the conclusion. However, you have conditional here and you have conditional here. Now you can do the same thing as we just did. So basically, in the first case, you are working with your first conditional. Why? Why are you actually doing this? Because again, you can kind of think backwards that you need to get to H or K. That is your end goal. And you can kind of see that you would if you could use, in this case, the constructive dilemma, right? The constructive dilemma would eventually give you this. If you were to be able to obtain this constructive dilemma from J to H and from J to K, and that together with your third premise would immediately give you what you need in your conclusion. But how do you get this? Well, you do need to get somewhere separately from J to H and from G to H and from J to K. And this happens to be already within your premises. It's just a question, how exactly do you achieve that? Well, this is how you achieve that. In the first case, you can assume conditional proof for the first premise, and then just basically assume G, and G through modus ponens gives you H and I, and that, by simplification, gives you H. Now, in a second, so now you've shown that based on our premises, we can get from G to H. That actually is one part of what you were looking for, right? Now, once you did that, here you can assume J for line 2. That through modus ponens immediately gives you K and L. You don't need L, so you just drop it through simplification and you got your K. So that shows you that you can get from J to K. And this is the two horns of your conjunction here, right? Which you needed for the constructive dilemma. So you can just connect them with a dot through conjunction, and that immediately through constructive dilemma, because of the assert premise, gives you H. Okay? So do you follow the logic here? But you see that like you can do it within an argument. That is more complicated than what we did before, but it's just something you really need to know for the future. Okay, so that's just an explanation on a slide of whatever I was already telling you right now. In case if you want to go back to slides, it's written here, but I guess it doesn't make sense to read it again. So the lines in the conditional sequence are hypothetical in that they depend on the assumptions stated in the first line. Because no assumption can provide any genuine support for anything, neither can any line that depends on such an assumption. So whatever you are working with here, those are just assumptions. You cannot use them here as just kind of you're doing these lines, right? You can only do it within your assumption. But based on the first and last line of your assumption, you can see that from this you do indeed get to line 7 in this case. When a conditional sequence is discharged, the assumption on which it rests is expressed as the antecedent of the conditional statement. The conditional statement can be used to support subsequent lines because it makes no claim that its antecedent is true. It just says if it was true, it would lead to where we needed to go. Right? So within here, we assume there are antecedent true, and we discovered that it does indeed, in that case, lead to our consequence. So we're not claiming it is actually true. We're just saying if. The conditional statement merely asserts that if antecedent is true, then its consequent is true. And this, of course, is what has been established by the conditional sequence for which it is obtained. You can also have the one sequence within another, right? So this is an example of something like this. Here, they started this by assuming L for the line 1, which immediately gives you the consequent here, right? But the consequent itself also is a conditional statement. So you can do another sequence assuming M in this case, which gives you M or. Then that, through modus ponens, gives you not N. Then that gives you O through disjunctive syllogism, right? N or O, not M, therefore O. And that you then go back because you proved that if M then O, so that's your line 9, but it still is conditional. That's part of this conditional. And through, you can change it through implication, right? Because remember, the rule says that implication, if it's if M then O, it's the same thing as if not M or O. And now that helps you to go back here and finally prove your conclusion, which was if L, then not M or O. So you got your L here, and you got your model from that on your first condition. So that's actually proving you the conclusion. Can you see that? Well, it's one of those things which, of course, you should try yourself in order to fully understand. But that's the idea here, right? We are first doing the assumption, but then within this assumption, we need another assumption. Both these assumptions on themselves don't prove anything other than the conditionals, but proving these conditionals then does prove our conclusion. Every line must be discharged. That's another reminder. You cannot finish like this. That is not allowed. So if you finished within the line and you never did this, right, this part, which brings you back, like what's your conditional assumption? What did it prove? Well, in this case, it doesn't seem to prove anything. You just ended here. That's a mistake. You can't do that. You have to go back to your argument and show what you have proven. Now next, 7.6 is indirect proof. Yeah, I know. Well, but they are not that long. I can't give the whole class lecture to just conditional proof. There's not that much there. Indirect proof is a technique similar to conditional proof that can be used on any argument to derive either the conclusion or some intermediate line leading to the conclusion. Consists of assuming the negation of the statement to be obtained, and then you basically show that it leads to a contradiction. Right? So since negation leads to a contradiction, that kind of proves that it is cannot be false. That's what it proves. Okay, so assuming it is true, then it has to be true in the end. We don't even know if it's true. But if assuming negation of it leads to contradiction, that is shows to us that the truth is preserved within the argument. Okay, so this is an example of indirect proof. Unlike with conditional, for the first line, AIP, assume indirect proof, right? So our conclusion here is not A. So we're assuming the opposite of that, which in this case would be A. If it was A, we would have assumed not A. But since it is not A, we are assuming A. And remember, we don't even know whether A is true or false. We're just assuming the opposite. Okay, then by addition, we get A or B, which is antecedent of our first premise. That immediately gives us C and D, right? We can drop D, we can go straight to C through simplification, and that, based on our second premise, gives us not D. Okay, that is great too. Then through we switch these two premises, right? We go back here, we switch these two because we need to show there is a contradiction, and then we can drop C, and that leads us to D. So we basically have not D on one line and D on the other line, which is conjunct to D and not D. That's clearly a contradiction. So we achieved the contradiction here. Can you see that? It cannot be that D and not D. Because if D is true, not D would be false. And then that will create a problem for us, because the whole thing then will be false. So since we have achieved this contradiction, we can say for sure that it has to be not A, because A within this sequence doesn't work. Right? And that is our conclusion. So indirectly, that proved our argument. It's not a direct proof, but an indirect, because if we are able to show that it leads to contradiction, that is enough for us. What? You think it is too difficult?
It is crazy. That's what it is.
Well, the good news is, like I said, I'm not going to ask you guys to do that on any of the exams. The bad news is, if you continue in logic, you will have to do it at some point. So just think about it kind of ahead of time and prepare yourself. Because definitely for 400 level logic classes, they will want you to do this stuff. Not exactly like this. That's another thing, though. because the rules could be different. I do want to talk next time about the way the other logic book does it, because I don't want you to be too shocked when, if you take philosophy with a different professor, you will suddenly discover that they are using different process. The idea is exactly the same. It's just the Hurley-Watson uses this. This is fairly simple and straightforward process. It could be more complicated depending on the book and the approach. Now, the important thing is, of course, to understand the logic behind it. And the logic behind it is the most important part. So I think that for introductory level, that is a great way to go. But yeah, if you go on further, that may get more complicated and more confusing. The correct word is confusing. Okay, so the process in direct proof begins by assuming the negation of your conclusion. So, but in this case, we would have to negate our conclusion, right? So if we were working with this one, for example, we could also assume negation of our conclusion. Now, it's easier, of course, if your conclusion is just one letter. If it's conditional, the better way to go is the conditional proof. But if it is just one letter, the better way to go is indirect. I'm just showing the principle is you assume the negation of it on your sequence here, and instead of assume conditional proof, you write assume indirect proof, so AIP. Since the conclusion is a negated statement, shortens the proof to assume A instead of not A. Although technically, yeah, if you are negating not A, you get not A, but this is the same thing as A. You write AIP. Since the assumption that leads to a contradiction is false, the indirect sequence is discharged on line 11, right? So this is a contradiction. Remember the contradictions when we talked about them. So if you do a truth table, what are you going to get for D and not D? False everywhere. It will be false. Well, in this case, there's just one letter, so it's just false. But if you got something else which is contradiction, which is longer, remember you would have false on every line. So that basically tells you it's a contradiction, it's always false. Like it's raining and it's not raining, which is exactly what this is. Imagine D is, it's raining. So that would tell you it's raining and it's not raining. Clearly a contradiction, right? Can't be. So that is why you've shown that if you assume A, it leads you to this contradiction. And that cannot be, so that gives you the right to assume not A, which is your conclusion. Yeah, so that is why on the last line you are again showing which line you are using, but instead of CP you write an IP, indirect. Here's another example. Now that is within the longer argument, right? To derive an intermediate line. You can derive an intermediate line the same way, basically. So at some point here, they do assume F instead of not F, and do the sequence which leads them to a contradiction, which helps them to establish not F. Why did they assume F in this case? Well, they needed it for the proof, right? For specifically what was happening in their proof. Which line was it? Yeah, for their conclusion, they needed not F and not K. And for the not F and not K, they needed not F. Because the conclusion is not F or K. So remember, working backwards, I guess in this case, if you were solving this from scratch, you would have to work backwards. You need your conclusion. Okay, that can be achieved through not F and not K, which of course for that you need not K and not J, but you also need not F. How do you get not f? Well, let's assume f. Let's see what happens within our argument. We assumed f, and through addition f or g, then that immediately through modus ponens gives us h and g. Switch them this way, just so that j would be on the left side. And then we drop h, so that is j through simplification. But line 7 has not j, so through simplification it is not j. So that is j and not j. So that's contradiction, so it can't be f. It has to be not f. And that is what they needed for their sequence. Okay, you see what's happening? So at any point in time, if you, for whatever reason, need some sort of letter, you can assume the opposite of that within your sequence and try to see, based on your premises, what's going to be happening. Does it lead to contradiction or not? Of course, it may not lead to the contradiction, in which case you'll be stuck, but that just takes a little bit more time than to work with your proof. And you can use both sequences depending on what you're doing here. So first they started with assuming conditional proof, right? They assumed L because their conclusion is if L, then M and P. Now great. That, based on the first premise, gave them the consequent of the first premise. But then they actually, instead of continuing with the conditional, they decided to go with indirect and see what happens there. They're assuming not M, and that leads to the contradiction, which means it can be not M, so not M, that's basically M. But M does help them to get to their conclusion. So that makes it faster. It actually, sometimes you don't need that. You could even write the proof without any of this conditional or indirect sequences, but then the proof would be much longer. And they have this actually shown in the book, like back to back, there are some arguments which become very much longer. Then when conclusion is a tautology. So in this case you have T or not T, which is a tautology, that would always be true, right? Indirect proof provides a convenient way for proving the validity of an argument having tautology as a conclusion. The only way in which the conclusion of many arguments can be derived is through either conditional or indirect proof, because otherwise you would not prove that. But here you can do it. So assume again the opposite of your conclusion, that it's not the case that T or not T. Remember that through De Morgan's rule, that means not T and not T, and that is T and not T. So that is a contradiction. So then not this, which we derive from that, right? That can be this. So that shows you that you actually have the conclusion. You see what I mean? You look kind of confused.
I'm gonna get it. It's okay.
Yeah, you need sometimes to do your own work. I mean, I don't know, like when you explain it, no matter how well you explain it, sometimes it's just impossible to understand until you start doing it. I know this very well, so that's why I'm like trying to also put up those videos, because when you start doing it, if you want to go back to what I was saying after you tried it yourself, that will be easier for you, and then you can, that's what he meant. Mm-hmm. Otherwise, it's like, what is he talking about? I don't know. So yeah, if the conclusion is a tautology, that's the only way to prove it. In other cases, you can prove it without going into indirect or conditional, but it's just going to be longer. It may take like many lines, and this is a nice shortcut way. So this is an example, like I said, indirect versus conditional. Now in this case, it shows to you that indirect is faster than the conditional. So same arguments, right? On the right and on the left. This one they were going with a conditional. You can do it, but it does seem longer, right? You end up with 14 lines. If we go indirect, that is faster. You achieve the same thing with 11 lines. Of course, it's better to have 11 lines than it is 14 lines.
Mm-hmm.
So indirect proof is better way to go. The conclusion, note A, are easier to achieve with indirect. Avoid this mistake. The reminder at the end of the previous section regarding conditional proof pertains to indirect proof as well. You need to discharge it, right? You need to discharge it. You cannot leave it hanging like this. That would be a mistake. You need to show what exactly did it help you prove that assumption. Okay, and then the last one, proving logical truths. 7.7. What's going on here? Both conditional and indirect proof can be used to establish the truth of a logical truth, which is tautology. Tautology. Tautology actually, I mentioned it before, by itself can be considered as an argument. Tautological statements can be treated if they were conclusions of an argument having no premises. Why? Because since it's always true, you don't need to prove it. It proves itself. But you need to establish the fact that it is tautology. You cannot just assume that, you need to prove that. So that would be where you are using one of these rules. So you see here we don't have any argument. We just have the conclusion, which is an argument in itself. Why? Because that is a tautology. But you need to prove it's a tautology. You can do it with a truth table, but that's just another way to do it. So in this case, you start with assuming conditional proof. You assume your P. Now, you also assume your Q in a separate line. Why? Because the P is antecedent for this whole thing, but the Q is antecedent for your conditional within here. So, okay, then you assume your Q. You immediately get your P. Well, that's from this part, right? This is the part which gives you your P. So then you can add P or P, and that is a tautology which shows you P. Okay, great. But that is just this part. So now you have to kind of go back. You got from Q to P, great. But that itself, based on already the whole thing, shows to you that that line also then would follow. So basically it tells you that as long as P is true, the whole thing is indeed going to lead you to always to be true. So that's a tautology. It is something which will always be true. You see the point? You understand the point? So if you just need to prove the tautology that it is a tautology, you can use the conditional proof. Or an indirect proof sometimes. So that's just repeating the same thing basically. Tautology is expressed in the form of conditional statements, most easily discharged through a conditional sequence, but if it wasn't a conditional here, you could use indirect proof. In some other situations, indirect proof. Well, here's a proof of the same statements using indirect proof. But that becomes much longer, right? And much more complicated. That's exact same thing. You are starting with if P, then if Q, then P. But you're going through indirect proof here, and that becomes very long. You are assuming the negation of the whole thing. Then you, through implication, do this within that, and through implication again do this, and then you use De Morgan's here, and you distribute your negation in another De Morgan and another De Morgan, and then you use commutativity here just to switch these two parts around, associativity, and then in the end you still get to P and not P, which is a contradiction. But it's just much longer and clunkier way to go.